Hello, welcome to a new live stream by the Research and Development Department here at Wolfram. My name is Jose Martin-Garcia. I'm a manager of a team of developers here at Wolfram, working on exacting projects such as geography, astronomy, the calculus of quantities and units, the calculus of dates and times. But today I am going to be talking about something I started doing almost 20 years ago during my many years as a researcher in General Relativity. And it is this suite of packages called xAct for efficient tensor computer algebra in Wolfram language. So this is the plan of the talk. I will start introducing xAct for those of you who do not know it yet. Then I will spend some time showing examples of how to use the two main packages of the system, the package for abstract computations called xTensor, and the package for component computations called xCoba. Then I will show examples of two of the other packages in the system, and then I will spend some time discussing frequent questions and future plans for the system. So because this is a live stream, feel free to post questions, both in YouTube and Twitch. You have chat windows to post questions, and I will address them as soon as I can or at the end together with this section. Okay, so let's start with the introduction to xAct. So this is a project that started back in 2002. It's all written in Wolfram language, which is very convenient for the type of computations that we have to do here with indices. And there is a little bit of C code for the more demanding computational parts. xAct is not a package itself. It's a collection of it's a hierarchical collection of packages. And currently there are 23 of them, and there are more being developed, so more soon. It performs both abstract tensor computations and component computations. I will explain in a moment what that means. And it's important also, it can do both at the same time. So you can mix those two types of computations. xAct is a mature and stable project. It has been successfully used in more than 800 publications already, many of them PhD theses or master theses. Just to give you an idea of the application areas, 47% of the articles citing xAct are in GRQC, 40% in high-energy physics theory, 7% in astro-PH, and the rest are in areas like condensed matter physics, fluid mechanics, differential geometry, multiple areas. So you see the variety of application areas for this. So to get an idea of these possible application areas, I invite you to visit this page, in which I collect from time to time the papers citing xAct. So here you have over the years the multiple articles that I know have cited xAct, and at the very end there is also a list of PhD theses. So here you have links to all of them. So I invite you to look at this and you get an idea of what can be done. There are in that list more than 950 different authors, which is a considerable fraction of the community. So I want to list here the authors with more publications in that list. And we have first Mohamed-Garoussi with an amazing 27 publications, then Juan Antonio Valiente and Alfonso Garcia Parrado following closely, Luc and Guillaume, Benjamin, then myself, Jan, Thomas, Johannes, Obina. So I want to thank you, all of you, and all the 950 plus authors for the continued support and the trust that you place in the system. And please keep using it. And it's main motivation to continue extending the system. So let me now go to the resources you have available for xAct. So the main place is the xAct web page. Here you can have You can then, you see the collection of packages there are right now. You can download tarballs for Linux and Mac or for Windows. There are installation notes. There are lots of documentations, other pages, a bit of history, links to interesting other pages on Tensor Computer Algebra, etc. So there is another page for contribution of other packages not listed there. So you can find here many examples. This is a page maintained by Leo and Teake. And yeah, there are many examples here. I also invite you to go there. We have a forum for questions right now with nearly 800 contributors, more than 1,000 posts over the years. So it's quite active. So yeah, feel free to send questions here if you use xAct. There are also questions in Mathematical Stack Exchange, but typically we handle them here. You will find more experts in xAct using the xAct forum. Okay. The structure of xAct, as I was saying, is a collection of packages, currently 23, and they are organized hierarchically. You will see that in a moment. When you load a package, all dependencies will be loaded too, so you don't have to worry about what depends on what. If you put together all these packages, there are more than 1,500 symbols, a third of them coming from xTensor, which is the core package. So there are lots of things to do and to learn in xAct. Okay, so let me give you an idea of what the packages are and do. So we have a collection of core packages. The main one is xTensor, the package for tensor computations. And then we have the tensor computations package. They both rely on permutation group theory, which is handled by this other package, and then there is some sort of tools package. We have then application packages. This is the section that is growing fastest. And then we have input-output packages to send things to tech or a GUI approach to xAct so that you can introduce tensors interactively. Okay, so there is a question saying, what are tensors? Okay, yes, I can imagine. I imagine I should have started. So these are tensors as they are used in differential geometry and in particular in general relativity. That's the main motivation. I am aware that the word tensor is being used recently in the numerical community and machine learning, for example, in order to refer to what I would refer as arrays. So multidimensional collections of data, typically numerical data. So here we are not emphasizing so much the numerical part, is more the symbolic manipulations that are needed in complicated computations in differential geometry and general relativity. Okay, so as I was saying, the structures of packages is hierarchical, and the way we organize this is by looking at this complicated graph. I mean, you don't have to actually pay attention to the individual lines, but the important thing to realize here is that all these dependencies are vertical. This is the way in which we avoid loops, right? And so we have the permutation group theory package here at the bottom. Then we have the abstract computations package, xTensor. You see how everything depends on that one. And then we have other packages, right? That various generations of packages that depend on other packages. And this is a tower that is growing with time. Okay. So, as I said, for those of you who don't know xAct, I will quickly show an example session of things that you can do. So the first thing you have to do is, of course, to load the packages. You choose which package you want to load. So here I'm loading xTensor, the package for tensor computations, and you see how it automatically loaded xPerm, so the package for computational group theory. The first thing you have to do in any computation is to define a manifold. So here we are defining a manifold called M of dimension 4, and we are going to be using indices with these names for the tensors in these tensor fields on this manifold. So for example, how do we define a vector field? And this is a vector field because it has just one index. So we do that. So V is now a vector field on the manifold M. Notice how I used A. Now I'm going to use minus A and minus B. As fundamental in general relativity, we distinguish contravariant vector fields and tensor fields from covariant vector fields in which the indices have a minus in front. This is now a rank 2 covariant tensor field on the manifold M, and it's antisymmetric in the indices minus A and minus B. Okay, so now we are going to define the other fundamental element always in general relativity, which is the metric field. So this means we have a metric whose determinant is negative. It's going to be called G. And of course, metrics are covariant tensor fields. And the Levi-Civita connection, the unique derivative which gives 0, torsionless derivative that gives 0 on the metric, is going to be called CD. So lots of things are defined together. We don't need to look at those. And now let's do some examples. For example, as usual, in the Einstein convention of tensor fields, we have automatic contractions of indices with repeated names, but of different characters. This is contravariant, this is covariant. So this is the delta. You see, it changed to VB. So internally, this is just V of B. We can apply, this is a product of the two vector field or two tensor fields, and we can apply the Leibniz rule, right? Just this one with the derivative of this one plus the other one with the derivative of the other one. We can now say, okay, multiply that by V with the index B. And because we know that this guy BC is antisymmetric and these two are equal, this term should disappear. And there is a super powerful function in the system called toCanonical, which will realize which terms are 0 and remove them. That's very typical. So this is probably one of the fundamental functions in the whole system. Okay, for those of you who know what this is, xAct uses throughout the terminology of abstract indices introduced by Penrose and nicely described in Walt's book, which is this book, Walt's General Relativity book, is the main inspiration for the whole system and notations and conventions. And when we extend to spinors, we follow another books called Spinors and Spacetime by Penrose and Rindler. Now, something that happens when you compare two books is that there are different conventions, typically signs, formulas related to Riemann and Ricci or other tensors. And so what we do in xAct is that we have this variety of dollar variables that can be changed to adapt to the conventions of any book you might want to compare. By default, they are 1, meaning they are exactly what Walt's book does, right? But you can change them at the very beginning. Don't change them in the middle of a session, because if you do, the whole system, the whole set of equations will get very confused, of course. Okay, so those are examples of simple abstract computation, right? So you are manipulating tensors, identities, in which you don't have to specify what the tensors are. You just specify properties of them, right? Symmetries, whether the indices are up and down, things like that. Now, how do we do component computations, right? Components, meaning here explicit values for the components of a tensor. For that, we have to load a new package called xCoba, the package for components in basis. And in the same way that we defined a manifold, here we have to define bases, also called frames or charts. And so we define the basis, and now we can do the following. We can define this tensor A and this tensor W. And the tensor A has rank 2, it's a matrix, and these are values defined in 2 covariant bases. Right? Each, you have to specify the basis for each level. And now we can refer to this guy, for example, right? So this is WB with components 7, 8, 9, 10, and it's an upper vector. Or A, which is this vector, this matrix, and you see it's antisymmetric. We can do computations as before, exactly the same notation, you see? And so instead of a dot operation, now the B index is contracted, this with that. And of course, we get a vector back, a vector which is covariant, right? So A is below the baseline. And if we multiply, again, we get 0 because we knew this matrix was antisymmetric, right? So multiplying, you don't have to worry about, should I put it on the left or on the right? The indices take care of all of that. Okay, so xAct is very powerful on this front. It can handle many bases at the same time. It will use different colors, so you can control which bases you are using. Notice also the fact that this is square, not the typical line here. So this is what it's telling you, for example, that this is a matrix. Here, in the standard notation, you wouldn't know whether this is a vector or a matrix which is 4 by 1. In xAct, if this was a 4 by 1, it would have another line there, right? So it would be like this, it would be a rectangle. Okay, and then we can do both together, which is something that is very alien to most other systems. Most other systems, you either do one or the other. You even have a switch to change from one to the other, but typically you cannot do both together. So here, for example, we can have our two tensors, the abstract tensors and the component tensors. We can say, okay, can I do something with it? And to canonical says, well, they are both antisymmetric. You can do nothing. So now, if we multiply these by these, you see, it realizes that these two can be multiplied into a symmetric tensor. And now, of course, because this is antisymmetric and this is symmetric, we do two canonical, and there we have it, 0 again, as before, right? We can do things like that. For example, you see, my vector was originally contravariant. If I require a covariant version of it, the system will introduce immediately metric components in the proper basis. You see, the red basis that we defined before. And now you say, okay, but now I know that this G, which was an abstract tensor, I know I want to replace it by an explicit tensor. For example, the Minkowski metric. Well, Minkowski, what this tensor really means geometrically will depend on what this basis is. Okay, so now you can do that, right? And you replace that thing by the component object, and you get back an explicit result. Okay, yes, so I'm looking at some questions. This is like Einstein summation convention. Yes, exactly. xAct is fundamentally an index manipulator, and it's fully based on the Einstein summation convention, indeed. There is one package, exterior, which is starting the use of index-free notations because they are very useful for differential forms, but that's kind of an exception in the whole system. There are more packages, yes, indeed. There are more packages to do component computations, right? This mixture of abstract and component computations is something that is more rare to find. Okay, so in xAct, everything gets a type, and what we will do now is to undefine things. So you can undefine your tensors, you can define your bases, you can define the manifold, you can remove the objects that were assigned, and at the very end, you can check that, voila, we don't have any symbols in the user space, right? Okay. So let me go now to a non-trivial computation, and from now on, I will go a bit faster. So we have to do the same thing. We have to define a manifold, define a metric. We have this metric, right? Yes, too fast. So I defined it to be met. It's called met, but I can specify that I want it to be printed as G. So whenever you write met, it will look like G. So internally it's still met. So that's the inverse metric. Of course, if the metric has indices staggered, it will be converted into the delta. And this is its Levi-Civita connection. So when you do this, then of course you get 0. That's the definition of the Levi-Civita. Now, every covariant derivative will have a variety of curvature tensors associated to it. So this is the Riemann tensor of CD. because we can have many covariant derivatives, we need to specify which symbol this is. Sorry, which covariant derivative this is. You can associate different symbols to different covariant derivatives. This is Ricci, this is Ricci scalar, right? Okay, if we contract indices in Riemann, of course, we get Ricci. If we contract indices in Ricci, we get the Ricci scalar. The system knows immediately all the symmetries. For example, if we permute the first two indices of Riemann, that's 0. If we reverse all the indices, A, B, C, D, A, B, C, D, and we subtract, that's the same thing, that's also 0, right? This type of permutation symmetry is known by the system. And if you multiply tensors and you get expressions with 100 indices, two canonical will be able to handle it too. Now, by default, Levi-Civita connections do not have torsion. We will see torsion in a moment. Okay, so now something important in xAct is how to convert tensors. So you have Riemann, and now you say, okay, I want to convert that into into partial derivatives of the Christoffel, right? So you get that. And look how these ugly indices appear. This is how the system handles dummies. So these indices will have a different number every time you evaluate this. And this is how we avoid getting indices repeated. We do this thing, the magical incantation, that is not there by default, so that you all are aware that this needs to be done. And once you do this, magically, you will not see these indices anymore. They are still there, but they are replaced in output. And so this looks much nicer. Okay, so let's go back again. So let's change the Riemann into Christoffels, and let's change then the Christoffels into derivatives of the metric. Okay, so we get that expression, right? Which is well known, kind of already a bit annoying for a variety of indices. This type of expansion is very useful because you can have arbitrarily large computations. You do this type of expansion and you check whether something is 0. For example, imagine that we have the first Bianchi identity, right? The fact that we permute cyclically the first 3 indices. So we do that, and now we do this trick. We expand into Christoffels, the Christoffels into derivatives of the metric, and you get that expression. Now you call two canonical as usual, and two canonical can figure out that this is 0. So we do the same thing for the Bianchi identity, which is a bit more complicated. It involves derivatives now. And right, so we can do the same thing. We convert the covariant derivatives into the the covariant derivatives into partial derivatives plus Christoffels. Now the Riemanns into Christoffels. So this grows already. The Christoffels into derivatives of the metric. So now this is too large and it triggers the output limiter. But to canonical, it takes now a second, but it will also realize that this is 0. Okay? So this method is just pure brute force and it's very powerful. Now with torsion, define a covariant derivative in which torsion is non-zero. By default, it's 0 if you don't say this. And now, of course, to avoid confusing it with the other derivative, we will use a new symbol. Okay, so now we have these associated objects. That's the torsion. And you see, before this would have given 0. Now it doesn't. That's the Christoffel, that's the Riemann, that's the Ricci. You see, it's always the combination of these standard names with the name of the derivative. Well, we say define a vector field, VA, as before. And construct the double covariant derivative and sort the covariant derivatives. And you see, now a Riemann is introduced. Now, the thing is that if we do the same thing with our derivative with torsion, a new term appears, right? This term is the same for the new derivative, but this new term appears with torsion, right? And so how is the second Bianchi identity now that we have torsion? Well, before we had to antisymmetrize this object, now we need another object with torsion, of course, right? So, well, again, we do the same trick. We convert to Christoffels. I did everything in a single go. So you see, there are all these steps. We get the outputs. The last one is 0. or the first Bianchi identity, right? We need now two terms with torsion rather than just the Riemann term. And again, we do the four things at the same time. We go to the end, that's 0. Okay, so these are just examples of non-trivial abstract computations of the sort that appear very frequently in general relativity. Okay, and again, I will undefine objects that will not need in the future to avoid confusion. Things in xAct cannot have repeated names. If you define an index called A, nothing else can be called L. If you have a tensor field called V, nothing else can be called V. From YouTube, are tensors just generate matrices to 100 dimensions, or there is something key I'm missing? Yes, that's a good question. So tensors are more than matrices. Tensors are geometric objects in differential geometry, right? So the question here is like a bit like, what's the difference between x squared plus y squared equal 1 and a circle, right? One is an equation. The other one is a geometric object. So tensors are geometric objects, and the arrays of components, the matrices you're talking about, generalized matrices, are like equations, right? And so there is more to tensors than just the array of components. Once you add information of bases, manifolds, etc., you have a complete geometric setting, and this has geometric information, geometric power. That's what is used in physical theories. Okay, so I'm going to finish with xTensor. It can do many, many more things, but I don't have time at all. Yes, so you can have many different metrics at the same time. You can have many tensor fields, many connections, or covariant derivatives. It's possible to work with conformal related metrics, induced metrics, product metrics. There are many more tensors that haven't shown. For example, the Einstein-Weil tensors, very important in GR2. There are other types of derivatives, like Lie derivatives, variational derivatives. You can work with other products. I'm just working with times here, but there are other products, say antisymmetric products to work with differential form. There are products to work with Lie brackets, things like that. You can work with inner, as in particle physics, with inner bundles, possibly complex. So there are an enormous number of things you can do with xTensor, and all its extensions. Okay, if you download xAct, go to this file, xAct documentation English xTensor doc, and you have full documentation, hundreds of pages there of things you can do with xTensor. Okay, let's move on to xCoba, the component computations. And this is going to look more like manipulation of matrices and arrays. Another question, how much does this share with linear algebra? Yes, good question. So this is multilinear algebra and multilinear calculus, right? So if you completely remove the derivatives from here, you have essentially multilinear algebra. Once you deal with derivatives, you are dealing with full-blown differential geometry. Let's call it multilinear calculus. Right? Okay. So we load the new package, xCoba. It realized that xTensor and other packages are already loaded, so it didn't reload them. If they weren't, it would have loaded them. And the first thing we are going to do is to now define a chart, so a coordinate system. So we are going to be working with the Schwarzschild metric, and our chart is going to be called SCHW. That's just a name. You can choose absolutely any name. It's going to be a chart on M, or at least on large enough region that you can work with it. So xAct is essentially a local computation system, not global yet. If you need to refer to components, we will use these numbers, 0, 1, 2, 3. And these are the scalar fields, and notice that these still have brackets. That's because they are scalar fields. They are going to be called this way. Now, as I said, every chart and basis has a color. It's going to be brown for us. And we are going to use a different typesetting for these objects than the default is. Okay, In xAct, you always get messages reporting which things are being defined. Okay, we are going to use a mass object, which we'll typeset as M. That's going to be the mass of our metric. And this is the metric, right? So if we write it like this, so yeah, it's a bit small. Let's see if I can do this bigger. Okay. So yeah, so that's a standard Schwarzschild metric in standard coordinates, right? So with diagonal form. So we can also write it in other ways, for example, right? So we just expand that object and you get this form, which is also standard. Okay, notice that we have just introduced this thing, but we called it met, but actually the system doesn't know yet that this is a metric. So if you try to get this thing with upper indices, it will complain, I don't know a metric yet. But you still can do things like for example, compute its inverse, right? So now these objects does have upper indices. For example, this is a contravariant vector, right? Just component 0, R, 0, 0. And again, I defined it to be contravariant, sorry. So if I ask for the covariant object, it will complain, I don't have it yet. But you can multiply with the metric, and then you get the covariant version of it. So now, how do we tell the system this is a metric? Well, we do this. We set this metric. We tell them, okay, it's using this chart. And sometimes it cannot figure out what's the sign. This may be completely symbolic. So we have to tell it, so it has 3 positive direction, 1 negative direction, 0 zeros. Okay, so now we can use both, you see, and it will not complain. It will automatically raise and lower indices as needed. This is very useful. And this is a contraction, right? But you see, the most important thing you have to notice is that this is using the exact same notation as the abstract computations, right? It's just that before this was a symbol, now this V just is this object, right? It's a tensor defined by components in some basis or chart. Okay, again, if we raise one index, we get the identity. And now, if you just write both indices up, it automatically presents the inverse metric, as we did before. xAct also is very careful with what is and what is not a density. And it uses Aztecar's notation with tildes. So by this, we know this is a 2 + 2 density, and it remembers in which basis this is a density. I don't have time to explain this, but this is much more powerful than the standard notation. This allows you to work with things like Jacobians and things like that. Very powerful. Finally, there is also the epsilon tensor, which is a tensor. You see, it doesn't have any tildes, and you can address components on this form. These are scalars. Again, I don't have time to work with this, but you can work both in the abstract computations and in the component computations with the epsilon tensor, the volume form. Let me see. Are there any examples of solving orbits around a black hole numerically? Well, that is a problem that comes later. So first you have to get to the equations. So xAct will help you get into the equations that you have to solve numerically, say with ND-solve, right? But I'm not going to show that. Can be done, certainly. I'm just going to show you the type of computations you need to do to get to the equations. Can metrics be arbitrary functions of ambient scalars? Yes, yes. You can put anything you want here. And actually notice that I'm still keeping here the brackets, right? That's because the metric doesn't have to be just a function of coordinate fields. It can be a function of any field you have, right? You can even have, I don't know, abstract contracted objects inside these things. As long as they are scalars and they are scalars corresponding to these bases you have specified, it's all fine. You can put here anything you want. Again, this is a system that goes much beyond others in how to mix abstract and component computations. Okay, so we have defined met. Remember, the met was a xTensor, so it's a tensor defined by components. Now we are going to get its covariant, its associated Levi-Civita. And again, it's an object that will say, okay, it's my partial derivative associated to this chart plus a Christoffel, and I will remember that it derives from this metric. So these three pieces of information are needed. But internally, you can forget about the internal structure, and this object can be used as exactly we did before. Remember how we were doing covariant derivatives of vector fields? It's exactly the same thing. And you see, we get now, of course, if we differentiate a vector field, we get a rank 2 object in which we have added the differentiation index at the very end. There are different conventions on how to do this. xAct follows what capital D, the main differentiation function in Wolfram language, does, which always is adding an index at the very end, right? So, of course, the covariant derivative of the metric is 0. We saw that before. And we can compute Christoffels, right? They have this form. Notice how xAct, xCoba rather, represents tensors of rank 3. So we have first the first index corresponding to A, then the second level corresponding to B, and then the third level corresponding to C. This is what matrix form does, and only with, again, the same idea that we have as many lines as levels, right? So first, second, third. In this case, they are both, no, the three of them using the same basis. That's why they are all brown, but they could have different colors if they were indices using different bases. Again, if you want to see it in a more traditional form, just change to differentials and partials. Okay, we can do computations. For example, commute the two derivatives on a vector field, right? So this is VC in both places, but this is BA and this is AB. So you get that result, right, which has three indices. Now, the standard way of writing this is just saying, okay, it should be that guy. And you see, we say, well, is that thing the same as this thing? Well, so far, equal doesn't know it, but we do simplify and we get true. What simplify did was essentially just moving this guy to the other side, putting them together with a subtraction, and then xCoba immediately realized that there is a way of moving these indices so that they match those. And then even though these objects look different, look at those zeros here, there are no zeros, they are actually the same. Just under permutation of indices. Those things are automatic. You can totally forget about transpositions, etc. That's the power of indices. Okay, being a Levi-Civita connection of a metric, this torsion is 0. Again, we could have added torsion, no problem. We can compute the Ricci, and it's 0. We know Schwarzschild is Ricci flat. Riemann is not 0. And again, notice how Riemann is represented. It has 4 indices, so it has boxes of boxes, right? The first 2 indices, the second 2 indices, etc. Okay. So that's Schwarzschild, which is pretty trivial. Let's work with Kerr-Newman now. And I'm going to define this. These are just settings to eliminate so many defining messages. I define a new chart, which is called Boyer BL for Boyer liquids. I define the 3 parameters, mass, rotation, charge, and I write the metric, right? We need to know what the metric is. So it has this form, and I just construct a xTensor. This is just a way of constructing a xTensor, as before. The important thing is that, again, we have the metrics, the 2 bases, it's defined, and this means this is not a tensor density. No? It has weight 0. Now, this is a very important function. This function is able to compute many, many, many things, and it does it in an optimized way, not repeating computations, and do parallelism, etc. So by saying all here, it will compute anything it can, including things like the derivative of Riemann. So it will use my kernels in the computer, and this will take about 10 seconds to compute. And as I said, this has computed all sorts of curvature tensors, derivatives of curvature, Christoffel's, base changes, lots of things. And it's all cached, so now it's very fast to access, right? So again, the Ricci scalar is 0, but for example, let's compute Riemann. So now, you see these little circles, these are things that are so large that are not typeset by default. And so you can just go to one of them and you see what the expression is. You can extract it too, of course. But this is a very useful presentation of the structure of the tensor, in which you see where the zeros are and which terms are 0 or non-zero. So that's Ricci. That's the Kretschmann scalar. You see, there are no computations here. It was all computed here in this step. So this is just fetching cached result. And if you want to extract a component, for example, the 0, 3 component of the Ricci tensor, meaning, okay, that's 0 minus a minus b. So that would be 0, 3. So we are getting that component, right? Is that component. Let's do a change of base, something also important. So we have been working so far with coordinated bases, but now we are going to change to a base in which the Kerr-Newman metric becomes diagonal, which is very useful. So we know this is the change of metrics, sorry, the metrics of basis change. And what we do is to define a new frame, which is now going to be colored blue. And we specify with this notation that the change from this frame to the other frame is this matrix. So now if you plot it, sorry, if you typeset the change, notice how it has two colors. That's because this first index, the A, is related to the blue basis, so frame. The second index is related to the other basis, right? It's a change of basis, so it needs to know about both bases to perform the change. So for example, this is the metric we had before from the previous slide. Now we change, and you see, we take indices C and D, and we multiply C, we convert it to A, D, we convert it to B, right? So these indices belong to different bases. These indices belong to different bases. These two correspond to the same basis of this and that, the red indices. So now we do that change, and you see, now our metric is the same metric, but in the blue basis. So with this simple trick, it's very easy to check and to keep track of which basis am I using, right? This is not a standard in the literature, which is always a headache, which to keep track of so many possible bases you might have. We extract the xTensor, and now we do the same thing again, metric compute. And voila, because this metric was now diagonal, it took 1.4 seconds to compute everything instead of 8 seconds. We can do the same thing, compute the covariant derivative, Ricci scalar is still 0. That's Ricci. If we put indices, we now check that, well, the diagonal components are non-trivial, but the metric is diagonal. Sorry, the Ricci tensor is diagonal, as was the metric. That's the Kretschmann scalar. And right, I added a full simplified at the end to show it in a simpler way. That's the Riemann, you see, and now it has a different structure of zeros. It has more zeros, actually. Okay, and we can do things like, for example, what's the symmetry, right? So this is a notation to check by, this object is rather complicated, right? It may have hidden structure. So we check it with this, and it says, okay, if you exchange indices 3 and 4, you will get a minus sign. If you exchange indices 1 and 2, you get a minus sign. If you exchange simultaneously indices 1 and 3 and 2 and 4, you get a plus sign. Okay, clean up again. And right, we removed everything we were using. We have no symbols, no objects in the global context. Let me see if there are questions. Maybe how does it work, for example, when there are internal and space-time indices, for example, in string theories of branes? Yes, so this can be done. I mentioned it in one of the slides, but I didn't show examples. So you can define internal bundles. So by default, when you define a manifold, it constructs the tangent bundle, which are the indices we have been using. So those are what is called the space-time indices. But if you can define internal bundles, possibly complex, as in particle theory. And then you can use indices of any time. You have the same tensor, you have curvatures, you have the equivalent of the electromagnetic field, the A, mu, etc., with internal indices, of course. So they are like Christophel's or Ricci rotation coefficients. You have all those objects. There are lots of examples about that in the documentation of xTensor. Yeah, that certainly can be done. Okay, so I'm going to show a couple of examples of perturbation theory, which is something that I know many of you like a lot. So we load the package for perturbations. It's called expert. Another pan with an X. Oh, yes. And notice some packages allow themselves to change the settings. So you have to be careful because sometimes a package will go and say, okay, I really like these other settings. So it changes a few things. So be careful with that. Okay, so again, we define a manifold. And because I deactivated the messages, we don't get any more messages. We define a metric, and now we are going to define a perturbation structure. This means H are perturbations of any order of the background metric G with perturbation parameter epsilon. Now we can do things like, if I perturb the metric to third order, how does it look? And it looks like that. So that's the background metric plus epsilon times the first perturbation plus epsilon squared with a factorial term times the second perturbation. So these two are perturbation orders. They are not powers. Right? These are powers. These are perturbation orders. Or you can just get the third perturbation immediately. Right? So that's it. Okay. So in order to distinguish, I always do this, which is to color the perturbation orders. And this can be done with this trick. Still the same thing. It's H. You see the two indices. And this thing called a label index, which is being used here to represent the perturbation order. Okay, so that's the perturbed inverse metric, right? So that's the inverse metric, the first order of the perturbation, the second order of the perturbation, the third perturbation. Now we expand the perturbations in terms of the original, right? And so this object, this is the perturbation of the metric, of the lower metric, with indices raised by the background metric, right? This is the standard technique in perturbation theory. So you use always the background metric, and indices are moved up and down in the object with the background metric. So that's what's happening here. And you see, we can go to the third order, for example, because that's what I specify here. You could go to the 10th order if you want. That's no problem here. So, for example, we perturb the metric, inverse metric, to second order. We expand it. And now, yes, so let's check something. So that's the perturbation of the metric to third order. That's the perturbation of the inverse metric to third order. And of course, if I multiply the metric and the inverse metric, the result should be a delta. So I expand that thing. There are lots of terms here. Now what I'm going to do, you see the explicit metric factors, I'm going to contract them. See how this B and this B could be contracted. So I contract them with contract metric, and then, as usual in xAct, at the very end, always to canonical. You do that, you get the delta that we worked on it, that was there before, and now we collect. That's a Wolfram language command. And you see, the result is the delta, as expected, plus terms of higher order than 3, of course, right? Residual terms of order 4, 5, and 6. Now, the interesting thing that is always done, and it is very important in studying perturbations of collapse in gravitational waves, whatever, is to perturb the curvature tensors. So we do the same thing we did before. We perturb the Riemann tensor. We expand the perturbation into the derivatives of the metric perturbation. And now we do the thing that all books do. These two terms, you see, have the same derivative. So just by sorting the derivatives, we can compensate one with the other. So we do that with sort code to canonical. We still have the Riemann terms here. If you want, for example, to particularize to a problem in which your background is Minkowski, it's flat, then you see That's a formula that's given in all books after some manual computation to first order. But of course, here we can do it to any order. We do the same thing. Now I do all things together, including the particularization to Riemann 0, and you get that, right? And again, I can go to third order. Well, that's going to take too long. I can do 3. I evaluate this. Well, that's a formula for third order, right? And I could go over. I know, let's do 4. Let's see how long does it take. So, right, so that's it. So that's a formula, again, on flat background for order 4. Okay, so yes, so something in passing, I will show. We know here there are these 4 terms, but with order 4. We know it, but construction. So how do you look for those terms here? So there is this useful function called color position. So we look for the positions of something that contains LE4, and we just color those positions. So we do that, and now we look, and here they are. Yeah, you see, at position 56 we have one, position 64 we have the other, and positions 93 and 94 we have the other 2. Exactly the same 4 terms of linear order hidden here, but for order 4. That's very useful. Again, clean up. And the last example I will show will use the xAct package, a package that extends many things of the core system of xTensor. Okay, written by Teake. So we define a metric again. Now we are going to change to avoid a complicated typesetting. We just say that all these tensors are written in this form with R's and G's. And what we are going to be doing is to take variational derivatives of various scalars, right? So that's Ricci, right? So that's the standard variational derivative. There is a formula here called var L, which will insert appropriately into var D determinants of the metric, right? So with the determinant of the metric, as usual in the Einstein-Hilbert-Lagrangian, this would have been given the Einstein tensor. Right? And so yeah, that's what we do. Right? If we take these square roots of determinants are being inserted, and so we get the Einstein tensor from this scalar. So that's Einstein-Hilbert. But now we can do more complicated Lagrangians. What happens with the Ricci square? Well, we do the same thing. That's the formula we get. We can do that, and here they are, right? So that's the new equations of motion for this new theory of whatever. We can do the Kretschmann, so Riemann square. We do the derivative. Look at that. So this is super useful when you are studying theories other than the standard yeah, right? And yep. Okay. So let's see. How would we get the curvature scalar? I think I don't understand the question. To get it from where? Okay, let's see. I have more minutes. So I have a list of standard questions that I receive frequently. And so many questions, of course, are, can you do this? And in many cases, the answer is no, because we haven't extended xAct yet to do that. A frequent question is perturbation theory of tensors defined in xCoba. So I've shown how to do perturbations of things like Riemann or Ricci. But what happens if I have actual component tensors? Well, that's not there yet. There is no special support for the combination of expert and xCoba. And I realize this should be added eventually. Of course, once you have the equations that you have obtained via perturbation methods, you can always expand them in a given basis. But that's doable now, but not these perturb the things that I already have in xCoba. Another thing that is very frequently asked is handling of general metrics specified by blocks. xTensor can handle what I call product metrics, which is there are blocks in the diagonal, but the off-diagonal blocks are all 0. That can be done right now, but when the off-diagonal blocks are non-zero, that cannot. That would be a general m plus m decomposition. That would be fantastic to have. We have something related, which is the m plus 1, what I call the induced matrix case. But this is using the full 1 plus m dimensional notation, not the ij notation of indices in each of the projected spaces, which is what people generally want. Yes, so xAct is very powerful on the manipulation of permutation symmetries, the sort of permute these indices and you get a sign. But there are other symmetries like the Bianchi identities in which you have multi-terms. And those are handled via joint tableaus generally. And we don't yet have full power functionality for that. Extras has some of the functionality needed, but this needs to be extended too. Other things that have been suggested is to collect many metrics, sort of take the books on xAct metrics and of solutions of the Einstein equation and collect them with their properties. It would be a nice project, but this is not done yet. Another thing that is frequently suggested is more functionality to explore a given metric, like how to classify it, how to find Killing vectors if they are there, etc. Yes, I said xAct is essentially a local computational system, should be extended to handle topology and global geometry. Tensors defined along submanifolds, like a tensor which is defined only along a curve, like the velocity of a particle moving. That's not there yet either, though there is a system for mappings. And so it's the beginning. The beginning of this extension is there, but it's not completed yet. Yeah, this we mentioned before. xAct is nearly always an index manipulator, but it would be good to handle index-free notation, as Exterior has started doing for differential forms. Support numerical work. This is, again, the question that was asked before about how to integrate something around a black hole. Yes, so it would be good to have the whole workflow from the Einstein equations to, oh, look how beautiful picture I get of something orbiting a black hole. As I said, what we can do now is to construct equations, but then you need to specify discretization methods or something else, how to solve the equations. Okay, so these are things that I know are not there, should be eventually, but not yet. Things that are there but could be done better. Well, some people seem to have problems changing from the abstract world to the component world, right? In principle, the idea is always, well, define the equations, but move via replacement to tensors defined via xTensor. That's my recommendation, right? And it should always work. But yes, probably we need like a simpler way to do that, like a specific command that does that. From a few years ago, there are even faster methods to manipulate permutation groups in the case that is needed in tensor computations, particularly for some complicated cases with a lot of symmetry. So Ben has found better ways to do that. So it would be good to have those methods, those new methods in xAct. And another thing that I see people having problems is that because xAct is designed for general relativity in mind, when people want to do problems with flat backgrounds, they have problems because they need to deactivate all the curvature tensors. And so again, probably we need a way to say, okay, forget about curvature, my background space is all flat. And then about bookkeeping and practical methods, I'm planning to move xAct to the new Wolfram Packlet repository to make easier the new releases. So you will just have to say update, or there is a new version, and it will update automatically. So yeah, the Packlet system is very powerful, and we should take advantage of that. Perhaps the code could be moved to GitHub so that we develop only the Wolfram language in .m or .wl files, rather than doing it in notebooks as we do right now. It would be good to have some place to collect known issues and suggestions. And another thing that would be good to do eventually, but it takes quite a lot of work, is to modernize the documentation. The documentation has the appearance of documentation of version 5. And so it's quite old. And so it would be good to change it to more modern looking documentation. Okay, so these are things Arnaud have been pointed out multiple times. I'm happy to discuss any of them if any of you wants to go deeper into any of these things. Again, if we don't discuss them here, you have the xAct forum. Go there, ask anything you want. We all experts in xAct are there, and we will try to help you as much as we can. Okay, and let me finish in the last few minutes I have. So xAct is a collection of currently 23 packages of Wolfram language code. It implements extensive and very efficient functionality for tensor computations. It handles both abstract computations and component computations in a coherent way, performing, when it's possible, component computations with the abstract tools, which makes the linking of them much more powerful and easy. xAct is very insistent in having a well-defined geometric meaning for everything. That includes things like Christoffel, Jacobians, etc. This is done just by keeping track of all the dependencies. Right? So these things that you read typically, the Christoffels are not tensors. Well, they are not because you forgot for where they were coming from. You keep track of the two covariant derivatives. They are related. They are perfectly well-defined tensors. So in this way, expressions are never ambiguous. You can take the Lie derivatives of Jacobians or whatever change of basis, it all works. It's all well defined. The strictness of the language allows blind attack of very large expressions. This is very powerful because computer algebra, if there is something that computer algebra does very well, is solving very large problems. And so, yeah, so this is very good for checking results, for getting the idea of where you are going, just do larger cases and to immediately see where this is going. I've used this multiple times in my articles to solve really large problems, and things like post-Newtonian computations to very high order, etc., are regularly done with xAct. xAct is very stable. It has been used for more than 18 years now. As I said, more than 850 references, including many PhD theses, sometimes with full appendixes of xAct code across multiple areas of physics and maths. They all were successful in the use of xAct. A very recent review by Michael McCallum on Tensor Computer Algebra features xAct as one of the highly recommended general systems. And well, if you try it, don't hesitate to ask directly to me or in the forum, and we will try to help. Okay, so that's what I was planning to tell you about today. Let's see if there are more questions. And again, if you find this type of live stream successful and useful, let me know and we will repeat it. We could talk about specific packages other times rather than a general overview of xAct as this one. We could invite other developers of those packages to talk here. And yeah, so I will wait a bit to see if there are more questions. So I have this question here from Harry about how would we get the curvature scalar, but I don't understand what you mean to get it from. So if you mean to get it, for example, from, say, the Kerniman metric, or yes, I think I should have it here somewhere. Yes, it would be a computation like this one, right? So I mean, I probably cannot now redo the whole thing, but because I don't have these objects loaded now. But if you just write here, Ricci scalar of CD bracket bracket, it will get you the Ricci scalar, which in this case is 0, of course. Go for a moment to the forum. Yep. So here we have multiple questions. This gives you an idea of things that are asked and things that can be done. Right? So let's see. So this was a question about how to eliminate those printed messages. Right. So these are questions about component computations, for example. And so this is something that we do typically. It's very useful when you send, rather than just asking a question, send a notebook showing what you tried, showing where you got stuck. And that's much easier to respond because it becomes very obvious very soon what should be done. Okay, I see no more questions now. So I think that should be enough for today. Again, if you have more questions, post them in the general community post about our live streams or in the xAct forum. Okay, that's all.